Alrighty, this is my extra credit for heat transfer for exam 3. So we were given that water at 100 degrees Celsius with a velocity of 0.3 meters per second flows over both surfaces of a flat plate that is kept at 20 degrees Celsius. So we were asked to find the film temperature, the Reynolds number at the end of the plate, L, and if it was turbulent, find the X critical value, find the velocity boundary layer at the edge, find the thermal boundary layer, delta T, find the flux at the edge, and the heat transfer per unit length. So what we were given was T infinity equals 100 degrees Celsius, Ts is 20 degrees Celsius, the speed of which the fluid is going at is 0.3 meters per second, and the length of the plate was 0.9 meters. So we started finding the film temperature, and it's basically the average of the plate temperature and the surrounding temperature. So you take 100 plus 20 over 2, but you need to do this in Kelvin. So this difference is going to be plus 273, which is approximately 330 degrees Kelvin. Now, once you know what the temperature of the water is going to be at, you go into the table A6, which is this table right here. So you come in at table A6, and you go to the values at 330, and you're able to find all the values except for the density. And the density is just the inverse of the specific volume. So you can just take the inverse of that and find out your value there. Let's get back over to it. So once you find all your values here, you can then start finding for the Reynolds number. The Reynolds number at the length L, so you would take your length to be L here. So then you end up with a value of a Reynolds number of 5.435 times 10 to the 5th, which in this case, because it's over 5 times 10 to the 5th, it is turbulent. So therefore, we have to calculate the critical value. When solving for the critical value, though, you use the Reynolds number of 5 times 10 to the 5th, and then you're able to manipulate the equation to where you can find X critical. And in this case, X critical is 0.828 meters. So then we were asked to solve for the velocity boundary layer, which is given the equation by 0.37 times, or 0.37x Reynolds to the negative 1/5. In this case, we're looking for the boundary layer at L, so it's 0.9. That gives us the boundary layer of 0.0237 meters. Next step, we were asked to find the thermal boundary layer, but given that this is turbulent flow, the velocity layer is approximately the same length as the thermal boundary layer, so therefore it's still going to be 0.0237 meters. We were then asked to find the local heat flux, and to do this you need to know H bar. So in order to solve for H bar, you need to you have to know your Nusselt number. So in order to find Nusselt, it's 0.0296 times the Reynolds number times the Prandtl number. The Prandtl number is found in the table. So then you come here and you start plugging in your values. We found that Prandtl was 3.15, and we used the Reynolds we solved at the start. It gives us a Nusselt number of 1680.95. So then you plug that value in for H. H is Nusselt times K over L. K is found in the table as well. And it gives us an H bar of 1214.02 watts per meter squared Kelvin. So once we know H bar, We can then put it into our heat flux equation, which is going to be h bar times Ts minus T infinity, which gives us a heat flux of 97,121.5 watts per meter squared. So once you know what your heat flux is over the entire thing, you can try to solve for your heat flux per length, which you just take your heat flux, multiply it by the length, you'll get Q. So in this case, Q is equal to 87,409.4 watts per meter. And that's it.